Now, next topic, that is continuous charge distribution. It implies that suppose we have a system of charges in which the distribution of charge that is continuous one. Then due to that particular continuous charge distribution, what will be the electric field at any point outside that charge distribution that we want to find. So let's first consider the linear, or we can say line charge distribution. Suppose as shown in the figure, on this particular line, charge is continuously distributed. And due to this particular charge distribution, we want to find the electric field at point P having position vector r with respect to the origin of Cartesian coordinate system. Suppose the linear charge density on this particular line charge distribution, that is lambda. Linear charge density means charge per unit length, that is lambda equal to total charge, suppose that is q, and total length is l, then we can write lambda equal to q by l. Its unit will be coulomb per meter. Now the concept here that we have to use like this, we have to divide this entire charge distribution into so many infinitesimal small line elements, so that each line element can be treated as a point charge. Then due to each one, if we find out the electric field at point P, and then after take the vector summation. Suppose one such small element dl dash is at position r dash with respect to the origin, and the charge residing on it, that is dq. So due to this particular dq charge, the electric field at point P, that is dE, equal to k dq upon magnitude r minus r dash cube into vector r minus r dash. Now this charge dq, that is on the line element dl dash, now linear charge density, that is lambda. So we can say charge per unit length is lambda, therefore charge on length dl dash is how much? So dq will be lambda at r dash into dl dash. Now this one is the continuous distribution. So here we can calculate the resultant electric field at P by taking the integration of this equation. So resultant electric field E, that is equal to K integration. Integration should be carried out over the line. So integration over line lambda at r dash into dl dash upon magnitude r minus r dash cube into vector r minus r dash. So this one is the resultant electric field at point P. Now at point P, if any charge Q is placed, then simply we can calculate the force acting on it, that is Q into this E. Simple thing. Clear? Now surface charge distribution, the concept is the same one. Suppose here as shown in the figure, for this given surface, the total charge residing on the surface is Q and the total area of the surface is A. So here we can write surface charge density, that is sigma, equal to Q by A, unit will be coulomb per meter square. Surface charge density means charge per unit area. Now here divide this entire surface into so many infinitesimal small elements. Due to each element, calculate the electric field at point P having position vector r. And then take the vector summation of all, we will get the resultant one. So suppose here one infinitesimal small surface element, that is dA dash. Suppose the charge residing on it, that is dq. So due to this dq charge, the electric field at point P, that is dE equal to k dq upon magnitude r minus r dash cube into vector r minus r dash. Now dq is how much? So per unit surface area, the charge is sigma. Therefore, on the given area dA dash, charge is how much? Simple unitary method. So we can write dq, that is sigma at r dash into dA dash upon magnitude r minus r dash cube into r minus r dash, k as it is. Now, to find out the resultant electric field at P, take the integration of this equation over the surface. Clear? So E, that is equal to k integration over the surface sigma r dash magnitude dA dash upon magnitude r minus r dash cube into r minus r dash. Clear? Now third, that is volume charge distribution. Suppose as shown in the figure, we have the volume V in which the charge distributed, that is Q. Concept is again same one here. First of all, we have to consider infinitesimal small volume element, and suppose that element is dV dash situated at position r dash from the origin, and charge residing on it, that is dq. Now, due to that, first of all, we have to find the electric field at point P having position vector r, and then after take the integration over the volume. So here, first of all, we have to take volume charge density, that is charge per unit volume, that is total charge upon total volume. So Q by V coulomb per meter cube. Now, electric field at point P due to charge dq, that is k dq upon r minus r dash cube into r minus r dash. But again now dq, that is volume charge density into volume dV dash. So dE, that is k rho at r dash magnitude dV dash upon magnitude r minus r dash cube into r minus r dash. Now take the integration of this one over the volume. So electric field E, that is equal to k integration rho r dash magnitude dV dash upon magnitude r minus r dash cube into r minus r dash. So in this way, one can find the electric field at any point due to continuous charge distribution. Clear? Now let's discuss the topic electric flux. Now see, we define electric field like this: electric field intensity at any point, that is the total number of field lines passing through unit surface area at that point perpendicular to that area. Now, electric flux, that is the total number of field lines passing through the given area normal to it. That is called electric flux. Flux means something is passing through the given surface. That is the concept of flux. In standard 11th also we studied about the volume flux, mass flux, means something is passing through the given surface. Here electric field is passing through the given surface that we have to consider. So this one is electric flux. Now suppose first we consider the uniform electric field as shown in this figure, and in that take a surface with surface area A, which one is placed normal to the electric field. So if surface itself is normal to the electric field, then area vector is always represented perpendicular to the surface. So area vector of the surface that will be in the direction of electric field. So here, suppose at this particular point, the electric field intensity is E. It implies that we can say now the number of field lines passing through unit area at that point, normal to that area, that is E. So if number of field lines passing through unit area is E, therefore number of field lines passing through total area A is how much? So that is E into A, and total number of fill lines passing through the given area normal to it, that is called electric flux passing through it. Okay, but see, always the surface is not perpendicular to the field. Suppose surface is a slanting one, means area vector of the surface is at angle theta with respect to the electric field. So if we take its component in the direction of electric field, so for this area vector, which one is making an angle theta with respect to field, have the component A cos theta along E. So A cos theta, that is representing the component of this surface which one is perpendicular to the field. So now here we can say the total number of field lines passing through the surface normal to it, that is EA cos theta. Suppose the surface is perfectly parallel to the field, means area vector is perpendicular to the field. So in this particular case, not a single field line will pass through the surface. Therefore, the flux passing through this one, that is 0. So now from all this one, we can generalize the equation for the flux phi, that is E dot A. Now E dot A, so that is EA cos. So EA cos theta. See, if area vector is parallel to electric field, cos theta, that is cos 0, that is 1. So we will get this particular situation. Then if the area vector is making an angle theta with respect to the field, then the flux passing through the surface will be obtained this one. And if area vector is perpendicular to the field, then theta equal to 90, cos 90, that is 0. So flux passing through the surface is 0. So we can write flux phi, that is E dot A. Flux, that is the scalar quantity. Clear? Now, suppose the electric field is non-uniform one, and the surface under consideration, that is also odd even surface. So in that particular case, if you want to calculate the total flux passing through that particular surface, then how to calculate it? Again, we have to divide this surface into so many infinitesimal small elements, and that element should be considered such a small so that for each and every point on that surface, we can consider the electric field that is uniform one. Such a small element that we have to take in consideration. Now, suppose for this particular surface element under consideration, the electric field is E. Its area vector, that is delta S, and suppose here the angle between these two, that is theta. So flux passing through this particular element, that is delta phi, equal to E dot delta S. So we can write E delta S cos theta. Now if you want to calculate the total flux passing through this one, then very simple, we have to take the algebraic summation of all this. And when here we are taking limit delta S tends to 0 means infinitesimal small surface elements, then in that case, we can represent the equation of total flux phi by integration also. So integration over the surface E dot ds, that is the total flux passing through that particular given surface. And here the unit that will be Newton meter square per coulomb. So this one is the concept of electric flux. Clear to all of you? Now Gauss's law, very important concept, very important topic. See, Gauss's law suggests this thing: the flux associated with any closed surface that is equal to the ratio of the net charge enclosed by that surface to epsilon 0. Let's derive this equation of a flux and let's try to understand this Gauss's law. Suppose we have a point charge q located at the center of the imaginary spherical surface having radius equal to r. And now consider that particular charge is at the origin, means the center of that spherical surface is at the origin of Cartesian coordinate system. Now suppose first calculate the flux passing through small surface element over that spherical surface. Suppose that surface element, that is delta S, it is situated at position r, the unit vector in the direction of r, that is r caret. Now electric field of charge q, that is radially outward. So at this surface the electric field that is radially outward, and the area vector delta S for this small element that is also outward, normal to the surface. So electric field and the area vector both will be in the same direction. Now, as per definition, we can write flux passing through this element, that is E dot delta S. Now E and delta S both are in the same direction. Now we can rewrite this one as E delta S cos theta, but theta that is equal to 0. So we can write E delta S cos 0 is 1, so that is equal to E delta S. Now if you want to calculate the total flux passing through this entire spherical surface, then take the summation of the fluxes passing through each and every infinitesimal small element of this particular spherical surface. So phi, that is sigma delta phi. So that is E is the same one at each and every point on the spherical surface, because each and every point that is at the same distance from charge q, and that is r. So E sigma delta S. So E into now sigma delta S. So if we consider this type of n infinitesimal small elements distributed over the entire spherical surface, and then after if we take the summation of all these one, we will get the total surface area. So total surface area for the spherical surface, that is 4 pi r square. So we can write now phi, that is equal to, now electric field due to a point charge at a distance r, that is 1 upon 4 pi epsilon 0 q upon r square into 4 pi r square. So here we can write therefore phi, that is equal to q upon epsilon 0. Now see this charge q that is enclosed by this particular spherical surface. So we can say the flux passing through any closed surface, that is equal to the ratio of net charge enclosed by the surface to epsilon 0. Clear to all of you? Now see one small application of it using, say, this Gauss's law. One can calculate the flux passing through any closed surface. Now here, suppose as shown in this figure, we consider a cylindrical closed surface and it is placed in the electric field E. Now suppose we want to find the total flux passing through this particular closed surface. Then consider these different surfaces, one this cross-sectional surface, second one this one, and third one that is the cylindrically curved surface. So here the cross-sectional surface areas, that is same one on both the side. So for these three surfaces, if we calculate the flux passing through each one, and then after if we take the algebraic summation, then we will get the total flux. Now see, suppose first we take flux phi1 passing through this particular first surface. So that is E dot A1. So that is EA cos 180, because area vector is always outward for the closed surface. So E and A1 both are in opposite direction. So flux phi1, that is minus EA. Similarly, flux phi2 passing through this second surface. So that is E dot A2. So that is EA cos 0, that is EA. Now suppose for this cylindrical surface we think, then phi3, that is sigma E dot delta S, that is infinitesimal small element. But here the area vector delta S and E are perpendicular to each other. So that is sigma E delta S cos 90 will be 0. So total flux phi, that is phi1 plus phi2 plus phi3, and you will get the resultant, that is 0. Clear to all of you? Now if we calculate the flux passing through any closed surface in this way, and then after suppose we want to calculate the charge enclosed by it or charge residing in it, then we can calculate using Gauss's law, right? Now with the help of Gauss's law, one can calculate the flux with the help of net charge enclosed by it, and suppose we calculate the flux associated with any closed surface by definition as discussed in this one, and then after using Gauss's law, if you want to calculate charge enclosed, then also we can do it. Clear? Now see, Gauss's law, that is very important one. Gauss's law is true for any closed surface, whether it is with symmetry or not. Here see, in this particular equation, the shape and size of the surface is not appearing. It implies that it is true for any type of surface. Clear? Then after, second thing, the term Q, this one on right hand side, that is the net charge enclosed by the surface. Net charge means if some charge is enclosed by it, positive, some negative, then we have to take the algebraic summation of all those charges to find out the net charge enclosed by the surface. Then here see, when we consider the surface to which we are applying the Gauss's law, that particular surface is called Gaussian surface. So if some charge is enclosed by it and some charges are outside the surface, but then also when we calculate the electric field at a point, then that will be due to entire charge distribution. This is the wonder of Gauss's law. You can consider the Gaussian surface arbitrarily as per your conveniency. And if some charge are inside the surface, some charge are outside the surface, then also the electric field calculated at any point, that is due to entire charge distribution. Clear? And this particular Gauss's law, that is very useful to calculate the electric field due to any symmetric charge distribution. And this Gauss's law also obey inverse square law. So later on we will discuss the applications of Gauss's law, and using Gauss's law we calculate the electric field due to symmetric charge distribution. At that time you will understand the importance of this one. Clear to all of you?